Hi everyone! In this video, we are going to present to you our Big Data Health project. We're going to implement machine learning techniques in predicting the medical appointment commitments, which mean if a patient shows or missed their appointment after scheduling it. My name is Lisa, and I'm a data analyst at Novo Nordisk. I'm accompanied here by Rohan, who is a data scientist at Green Lake Technologies, and Nandini, who is a data analyst at Dime Community Banks. We are all graduates from St. Peter's University. This project attempts to predict whether or not a patient will attend their scheduled appointment. Approximately 25% of all appointments in the set were no-show data. If this is representative, this is a substantial cost in clinics in terms of wasting hours of doctors and the staff, as well as the patients who are waiting for their appointment time. The project is aimed to help clinics and hospitals in understanding what attributes are associated with the individuals who did not show up. So this is our agenda for today. We will first go over what and where the dataset is coming from, then explain the pre-processing, which will lead us into our data analysis. Lastly, our machine learning techniques used and the result that it achieved. The data source is from this link here on Kaggle, and the dataset was credited to Johnny Hopton. It contains 410,000 observations with 15 variables. Status is our predictive variable, meaning it is a variable we're trying to predict. Age, awaiting time, handicap are the numerical variables, and the rest are our hierarchical variables. The language used here was PySpark. In the dataset, there are questionable data points such as negative age and some flagged fields, including numbers that are greater than 1. These needs to be cleaned up. So how do we pre-process the data? Well, first, there are many spelling errors in the data, so we use MapReduce to fix this error. Next, there were null variables that had to be replaced by either the average of the column or by the mode. Lastly, there were some data issues, such as the age being a negative number or appointment registration date that appear before the scheduled dates. There are a few features that we looked at that may have contribution factors to the predicting variable. First, we look at the day of the week of no-show patients. Here we can see there isn't much of a difference between the day of the week for it to be a significant factor. Next, the feature of the gender of the patients. There's no obvious difference between males and females for shows and no-shows. It's worth noting, however, that females are the majority of the data, skewing it towards the female respondents. From these appointments, 67% showed up for females, and male showed up at 72% of the cases. This is slightly more than the percentage of female who will show up. Lastly, the age. The difference between shows and no-shows in terms of age pops up right away in visuals. There's no-show skews more than the left, showing younger patients are more likely to miss their appointment. Now, onto the data modeling. There are 3 different binary classifications that were used in this project: logistic regression, decision tree, and random forest. With a given data set, it fits into the classification category, where we are classifying if a patient will show or no show. The dataset was split into 2 different sets, training and testing. There are 3 different steps that were taken for building this model. First, an initial model is created with the training set. Next, the parameters were tuned using paragrid function, and 5-fold cross-validation were used to estimate the skills of the model. From those 5, we evaluate which of the 3 binary classification models was best used for the testing dataset. Random forest gave us the best result out of the 3, with an accuracy of 73.9% for testing. With a given dataset and the available features, the predictive model build shows potential, with an area under the curve greater than 75%, but in practice is unstable. The given variables are not strong enough predictors. Now let's dive deeper into the code. So PySpark was done in Databricks. First, we import the data file and look at the data type. Next, we look at the count function. Here, we know that there is 410 observations in this dataset. Then we imported important libraries for this project, such as NumPy and Pandas. After that, we built the schema of the dataset, where we are fixing the spelling errors of the feature label and replacing it as new columns using the reduce function. The describe functions shows the stats as well as the null values in smokes, tuberculosis, and awaiting time. As you can see here, there's a negative number under age, which is the data issue. Now, this is where we're going to fix that data issue where the age is less than 0. So we filter them out to find which observation have this error. Next, we are replacing the null values and general assumptions. If a patient don't input anything for smoke or tuberculosis, we assume they do not have it, hence 0. For wait time, we took the average of the column. Now we have our dataset ready and clean for exploratory data analysis and binary classifier. These are the graphs that were explained in the PowerPoint. So moving forward, we're going to go straight into data modeling. Here we import a few libraries including Pipeline and One-Hot Encoder Estimator. For simplicity's sake, we will use the One-Hot Encoder to convert all categorical variables into binary vectors. It is possible here to improve prediction accuracy by converting each categorical column with an appropriate method. Here, we use a combination of the string indexer and One-Hot Encoder Estimator to convert the categorical variables. The One-Hot Encoder Estimator will return a sparse vector. We use a vector assemblator to combine all the feature columns into a single vector column. This includes both the numerical column and the One-Hot Encode binary vector column in our dataset. Run the stages as a pipeline. This puts the data through all of the features transformations we describe into a single cell. The goal of the ROC graphs is to tell how much a model is capable of distinguishing between classes. Our goal is for having the line not touch the middle. Here, we are keeping the relevant columns in our dataset, which are the label and the features. In labels, if it's a 1, it indicates that patients are showing up to their appointment, and 0 for not showing up. And next, we split our data into training and testing, 70% for training and 30% for testing. Now, let's get into our first model, which is logistic regression. We're trying to fit our logistic model on our training data, then make predictions on the test data using the transform method. We can use the binary classification evaluator to evaluate our model. Note, the default metrics for the binary classification evaluator is area under ROC. The training dataset had an accuracy of 61%. We use 5-fold cross-validation to estimate the best fit for the models 5 times. From those 5 folds, we choose the best fit to predict the test data and result with an accuracy of 61% for testing as well. Next, our next model is our decision tree. Similar to logistic, we fit the model and evaluate using 5-fold cross-validation. The difference here is that we extract the number of nodes in our decision tree, as well as the tree depth of our model, which starts with 3 nodes and a depth of 1. We made the prediction on the test data using transform method. Looking at the prediction and probability of each prediction class, we got an accuracy of 30% for our training data. Again, using 5-fold cross-validation, we chose the best model with 23 nodes and a depth equal to 6. That brings our testing data to 56% accuracy. And last but not least is our random forest model. Similar to the previous two models, we are trying to fit the model on our training data, look at the prediction and probability. The binary classification evaluator gave an accuracy of 73% for our training. And again, using the 5-fold cross-validation, we choose the best model and result in 74% accuracy for testing. As we see in comparison of the 3 classifications, Random Forest has the best accuracy and generate prediction for the entire dataset without training and testing, which results in the accuracy of 74.6%. While some no-shows can be predicted with accuracy above chance, it's a small population. The model possibly has potential to be used to target for additional reminder messages for patients that are identified as to not likely to show up. The most important predictor of attendance were the age of the patient and the number of days between setting the appointment at the actual appointment date. Younger patients are less likely to show up, and longer wait times are associated with no-shows patients. SMS reminders and having insurance were associated with slight improvement in show-up rates. That is the end of our project. We hope you enjoy our video, and thank you for watching.